All right, so let's spend the majority of our time today going through this exam from fall 2019, exam 3. Help you prep for your exam 3 on Wednesday. I'm going to skip the true false. You can certainly discuss those with each other. They are things that you should know from facts about derivatives and the mean value theorem, for example. Number 5 is technically one you don't need to know, though I will tell you it's fairly easy. It doesn't look so easy. When you differentiate an integral like this, essentially it's like the derivative symbol and the integral symbol cancel. And this entire thing simplifies just to the integrand function, the e to the sine function, though you do put the variable there in here. You don't use u. I will just tell you that as something that you'll need to know if you take calculus 2. It's like the derivative and integral undo each other. But you're not responsible for that on your exam since we didn't really have time to talk about it. But let's talk about the types of problems that you should be able to do because we have talked about them. This one looks hard. It's supposed to evaluate that integral. However, I give you a hint in such a way that it's actually easy. I say that notice if capital F is sine of x squared, then its derivative you should be able to compute by the chain rule is this, 2x cos x squared, right? That's sine of x squared, that's a composition. If I told the people on this old exam what the derivative was, but you should be able to find that if I asked you. It's the chain rule, take the derivative of the outside function, the sine function, to get cosine, plug in the inside function x squared, then multiply times the derivative of x squared, which is 2x. But because of that, this integral, even though it looks difficult, is actually easy to do. Remember, by the fundamental theorem of calculus, this is the capital F function evaluated from 0 to the upper limit of integration, square root of pi over 2. And remember what this notation means is you first plug in the top number and then subtract what you get when you plug in the bottom number. So that's the actual calculation we have to do. By plugging, first of all, square root of pi over 2 into the capital F function. So we get sine of square root of pi over 2 quantity squared, right? Because this function's sine of x squared. And then we subtract sine of 0 squared. And this is set up to work out nicely. The square root of pi over 2 squared is just pi over 2. Sine of pi over 2 is 1. You can double check that with your calculator. Sine of 0 is 0. The answer is 1. So we got a problem here that looks difficult at first glance. But if you know the fundamental theorem of calculus and are just careful plugging numbers in, it works out pretty nicely. Let's double check it with Mathematica. I'm trying to integrate from 0 to square root of pi over 2, which I can type in there like that. I make the pi by doing escape, p escape. The function I'm integrating is what you see over here. Where'd my cursor go? Lost my cursor. There it is. Okay, the function I'm integrating is what you see over here. 2x times cosine of x squared. This should equal 1. It does. Okay. You should know the geometric meaning of that as well. If I plot this function that I'm integrating over the interval from 0 to square root of pi over 2, if the graph is always above the axis, which it actually will be here, then the area under the graph equals 1. You can't tell that just by looking at that picture, but the area under that graph, because of this calculation, does equal exactly 1. Number 7 is about properties of integrals, abstract properties that you should know besides the fundamental theorem of calculus. In particular, this problem, I'm testing the linearity property. I'm trying to find this integral here, the integral of what you would call a linear combination of f of x and g of x, 4 times f of x minus 8 times g of x. That is the corresponding linear combination of the individual integrals. It's 4 times the integral of the first function minus 8 times the integral of the second function. That's a linearity property of integrals. There's a linearity property of derivatives as well, right? Because the derivative of 4 times f minus 8 times g would be 4 times f prime plus or minus 8 times g prime. That's a linearity property of derivatives. Integrals have the same kind of linearity property. You just factor out the constants, and this minus sign becomes a minus sign there. Now just use what you're given. You're given that this integral is 11 and this integral is negative 4. Just plug those numbers in there. 11 in place of that integral, and negative 4 in place of this integral. Careful about signs. This is 44 plus 32. The answer is 76. By the way, I didn't do this, but I'm not ruling it out for your exam. Sometimes you should know, well, you should know, I'll just say, other properties of integrals that could be useful here. I could have said, assume that the integral of f, first of all, from 2 to 0 is maybe 4, and the integral of f from 0 to 3 is 7. I could have started with those two pieces of information instead of this one. There's another property of integrals that would say that this integral right here is the sum of these two. This kind of property was on the quiz. It's the sum, the integral from 2 to 0, plus the integral from 0 to 3. And then you'd plug in the 4 and the 7 to get 11, and then you'd plug the 11 in here just like before, and ultimately get still the same answer of 76. Okay, so you should, if I give you this kind of assumption ahead of time, instead of that assumption, you should be able to still combine those properties in this kind of way. This makes intuitive sense if you think about pictures. If you imagine your graph is always above the axis, which it doesn't have to be actually, but if you just pretend it is, just for the sake of simplicity, this is saying the area under the graph between -2 and 3 can be split up into two pieces. The area under the graph between -2 and 0, this part right here, plus the area under the graph between 0 and 3, this part right here. If that's 4 and that's 7, then the total area under the graph is 11. Make sense? So, I mean, you can certainly write these formulas on your note card, but to tell you the truth, if you think about them intuitively with pictures, that helps you understand them and probably remember them better than just spending too much time searching through your note card. And remember, I always say note cards are just there for security, just to help the anxiety be lower. You should study hard enough that you are confident you can do the exam without a note card. That's the kind of studying that you should do to do your best on the exam. Otherwise, you spend too much time looking through your note card. It should be there just for your security. Just doing integral problems here at first. This one is a L'Hopital's rule problem. We'll come back to it. Where's another integral problem? It's not on this page. Number 11 doesn't look like an integral problem, but it actually is. The velocity of a particle along a straight line in feet per second is given by this function. That's a velocity in feet per second. No, could have used meters per second, could have used miles per hour, whatever. The units don't matter as long as they're units for velocity. Using the fact that this function is an antiderivative of little f, show work to find the change in position, also known as displacement, of the particle from time 1 to time 3. So it's a fundamental fact to know here about integrals that the integral of the velocity gives you the change in position over whatever time interval you happen to be talking about. Change in position, symbolically represented by, oops, spelled position wrong, change in position symbolically represented by delta capital F. If little f is the velocity, its antiderivative can be thought of as the position, at least if you choose the origin appropriately. This would assume you start at position 0. That change in f is going to be the integral of its rate of change. That's what the fundamental theorem of calculus says. Usually you use the fundamental theorem of calculus to evaluate integrals, but here we're really using it to find a change in position. And actually, because I'm giving you the antiderivative, you don't actually have to write the integral symbol unless I asked you to. It would be the integral from 1 to 3 of the velocity. But wait a minute, by the fundamental theorem of calculus, that's capital F of 3 minus capital F of 1. So I don't really have to write the integral symbol here to solve the problem. But I think it's worth writing it anyway to remind yourself that the integral of the velocity is the change in position. But hey, I find that change in position by doing the subtraction. I gave the people on this test from 2019 the formula for capital F. I didn't have to. You should be able to figure that out. I mean, it's a little tricky. You've got to figure out an antiderivative of that. And find an antiderivative of 5t. You're going to have to raise the exponent by 1 to get a t squared, but also divide by 2. Because if you differentiate that, you'll have to bring the 2 down and it'll cancel with the 2. And the integral of t cubed, you've been working on these integrals, is going to be 1/4 t to the 4th. And the minus sign here becomes a minus sign there. So I gave them the antiderivative, but technically I didn't have to. They should have been able to find it as well. Anyway, now you just plug the numbers in. So plug in t equals 3 first to get 5 halves times 3 squared minus 1/4 times 3 to the 4th minus, in parentheses, what you get when you plug in 1. 5 halves times 1 squared minus 1/4 times 1 to the 4th. Biggest mistake people make on this kind of stuff is with sign errors. This needs to be a minus sign here. There need to be minus signs here and here as well, and you need parentheses around this thing because you're subtracting the entire quantity. Anyway, here, let's see, this becomes 45 halves, 9 times 5. 3 to the 4th is 81. I get 81/4. Bring this minus sign through the parentheses. I get a minus 5 halves and a plus 1/4. I'll go ahead and combine 45 halves minus 5 halves. That's going to be 40 halves, which is 20. And then minus 81/4 plus 1/4 is going to be minus 80/4. That's minus 20. And the answer is 0. Is that wrong? Well, if I haven't made a mistake, it's not wrong. Change in position can be 0, even though you've been moving. You move one way, then you move back the other way. If you end where you started, then your change in position is 0. So that certainly is a possible answer. And you still would use units of feet here, by the way, 0 feet. But did I make a mistake? I think I did it right. Let's double check it by doing the integral from 1 to 3 of the little f. That's the 5t minus t cubed. The answer is 0. Looks like I did it right. What's really going on here graphically? If you graph 5t minus t cubed over the interval from 1 to 3, it'll go both above and below the axis, like that. The area under the graph between t equals 1 and t equals 3, well, the graph is above the axis. That means the change in position is positive. The object is moving in the positive direction there. The velocity is positive, I should say. So yes, the change in position is positive as well. But then once you get past time equals 3, the velocity becomes negative. The particle is turned around and is going back the other way. And evidently this area right here is canceled out by this area. They're equal areas, but one is below the graph when it's above the axis, and one is above the graph when it's below the axis. So you think of this as contributing positively to the integral, and this is contributing negatively. And evidently, they end up canceling each other out exactly. That didn't have to happen. It just did. That's the way it turned out here. It's possible to get a negative change in position. That just means you are if the right word is positive direction, and your negative change in position would just mean you're to the left of where you started. That's all it would mean if you're moving back and forth left and right. Can I clarify anything? Please stop me if you want me to clarify something. Skip 12 and 13 for the moment. Here's another problem about integrals. Looks kind of complicated. Lots of words, got a graph, confusing looking equation. Take a breath. It's not as hard as it looks. Like I emphasized last Friday, using your imagination is very helpful. This graph below shows a net flow rate. It's really the graph of a derivative, even though you don't see a prime here. You don't see an R prime. So because you don't see an R prime, you're like, why would this be a derivative? Well, just pretend it's the derivative of some function. Maybe I should call little r, maybe I should call it capital R prime. Or capital R then would be some other function whose derivative is little r. I can do that if I want. It's okay. Capital R prime is little r. It equals, if I let V equal capital R of t, evidently maybe capital R represents the actual volume, then the derivative dv dt is little r, where I'm assuming little r is capital R prime. Okay? It's important to realize that kind of thing can be thought about that way. But this is the graph of little r, the flow rate in gallons per minute. It's telling you how fast water is flowing in and or out of the tank, net-wise. When the graph is positive, like it is between time 0 and time 2, that means net-wise water's flowing into the tank. Now, it's possible that your tank, it's got a drain at the bottom. You've got a faucet up here. It's possible water is both flowing in and out at the same time. But when the flow rate is positive, that means it's flowing in faster than it's flowing out. When the flow rate is negative, like from time 2 to time 3 or time 4, then it's flowing out faster than it flows in. So during this time period, the tank is filling up. It's getting bigger in volume. And during this time period, it's going down in volume. It's really, really important, if you're going to get this, that you think about that conceptually in the way that I just described. The integral represents the net change in volume. You could call this delta capital R if you like. I didn't, but you could. You could also write it as capital R of t minus capital R of 0. It's the change in R, capital R, from time 0 to time t. All right, that's just the background. Part A. What is the change in volume from time 0 to time 4? That's just going to be capital R of 4 minus capital R of 0. That's what the answer is going to be. But I don't have a formula for capital R. I don't have a graph for capital R. What I have is a graph for little r, its derivative. The Fundamental Theorem of Calculus, FTC, says that's the integral of its derivative from 0 to 4. It's the integral of little r, whose graph I do have. And by the signed area interpretation of the integral, this integral is going to be the area under the graph when it's above the axis minus the area above the graph when it's below the axis. This is going to be 9 minus 5 is 4. Don't forget units, gallons. Does that make sense? The confusion comes just from all the symbols and all the relationships going on here. It's confusing, what is little r, what is capital R, to think about. But if you keep your wits about you and rethink about this before Wednesday, you realize you really don't have to do much. Just do 9 minus 5, do this integral, and the answer is 4. That's the net change in the volume from time 0 to time 4. If it was from time 0 to time 2, then the change in volume would be 9. There's 9 more gallons in the tank at time 2 than there was at time 0. If it was from time 2 to time 4, then the answer would be -5. The volume goes down by 5 gallons from time 2 to time 4. If I assume that the initial volume is 2 gallons, what is the volume at time 4? Just take the initial amount and add the change, that's all. Volume at time 4, V equals capital R of 4, I could think of as being the initial volume, V0, plus the change in volume. That thing right there is the change in volume. This would be 2 plus 4 is 6 gallons. This is a really easy problem, actually, if you know the concepts. Can I clarify anything here? Understanding the concepts means, well, first of all, knowing the things I've told you, like the fundamental theorem of calculus and how to interpret the integrals with areas. And then secondly, it really is helpful to use your imagination. Imagine this tank, water flowing in, water flowing out. Over this time period, it fills up faster than it drains. And over this time period, it's draining faster than it fills up. Or maybe during this time period, you've shut the drain and you're just turning on the faucet. By the time you reach time 2, you've turned off the faucet, then you open the drain. The water goes up, then it comes back down. 18 you can skip. I guess that's it as far as, no, there is one more problem about integrals, excuse me. Actually, a couple more problems about integrals. I missed them here. Number 15 is about integrals. And in fact, what we talked about last Friday, density functions or probability density functions. You can use either name for it. We call them probability density functions when we apply them to probability, but you also can just apply them to modeling data and not think in terms of the concept of probability. But they are related to each other. Part A is a conceptual question. Where are the data most dense? What does that mean? This is related to what we talked about last Friday. When you graph these PDFs, probability density functions, or just DFs, density functions, the data is going to be most dense where the graph is highest. That's why it's called a density. If you graph this function 1/5 minus 1/50th x over the interval from 0 to 10, what does it look like? Well, it's a line with an intercept of 1/5 and a slope of negative 1/50th. Something like this, maybe. Or that's 1/5, 0.2. And how high is this function going to be when you reach 10? I guess it's not an accurate graph because it's going to be down to 0. Okay, scratch that out. When you reach 10, the function is going to be down to 0. Plug in x equals 10 there, you'll get 0. This is the graph of this PDF. It's highest right there at 0. So in other words, it's highest overall near 0. The data are going to be most dense near 0. There's the answer. The choices were low values, medium-sized values near 5, or high values near 10. This graph is highest near 0. That's the answer. If I had had a different graph that went up like that, then it would be highest near 10. Or if I had a graph that maybe went up then down, then it would be highest, most dense in the middle. If you do simulations with this, like on Mathematica, like I showed you last Friday, most of the data is going to be near 0. Very few will be near 10. I could do another simulation if I wanted to, but for sake of time, I'm not. This is a useful thing. People use these kinds of models all the time. Certainly actuaries do in insurance companies. Other people do, scientists, engineers use probability models a lot. How do you find probabilities once you've got this density? You integrate it over whatever interval you're interested in. I don't ask that here. I could have. I could have said, well, okay, let's do part B first, and then we'll find a probability. Part B, the function capital F equals this is what you call a cumulative distribution function, a CDF. It is an antiderivative of the PDF. The notation capital F is on purpose. Capital F prime would be equal to little f, right? Just double check it. Differentiate this. You get 0.2, which matches that 0.2. Minus derivative of this will be minus 0.02x, which matches the 0.02x right there. Capital F prime equals little f. Okay, I phrased the problem differently back in 2019. Find an approximate percent of data less than or equal to 5. That is the same as the probability that a randomly chosen data point is less than or equal to 5. I could write probability notation here like we did last Friday. I could write that. How do you compute this? The way you do it is you integrate the PDF over the interval, in this case from 0 to 5. But by the fundamental theorem of calculus, that's the same as capital F of 5 minus capital F of 0. It's the change in the value of the CDF. So just do that calculation. Capital F of 0 is 0, so I really only need to figure out capital F of 5. Sorry, it's a little hard to see here. That's a 1/5, plug in x equals 5, minus 1 over 100 times 5 squared. This is 1 minus 1/4. The answer is 3/4 or 75%. 0.75 or 75% of the data is less than 5, or I can think of that as a probability. The probability that a randomly chosen data point is less than 5 is 75%. Should make intuitive sense. We've just found the area under this graph from 0 to 5. We know the total area under it has to be equal to 1. That's the necessary condition for a PDF. But because the graph is high over here, this is going to be more than half the area. In fact, it's 75% of the area. Very common kind of application of calculus. 16 is also about integrals. physics, consider the motion defined by parametric equations, x equals t and y equals t squared. Part A, use your calculator to help you draw the parametric curve. Right down here. I could also plot points. I could make a little table. I'm not requiring them to, but if I asked you to, you should be able to. Make a table of values. First for t, and just for the sake of interest, let's do it every half unit for t. Look at the formulas, x equals t and y equals t squared. You've got two functions, f and g, that tell you the x coordinate of the point and the y coordinate of the point. X equals t, so that's real easy. Y equals t squared, so I got to compute the squares of these things. 0.5 squared is 0.25, 1 squared is 1, 1.5 squared is 2.25, and 2 squared is 4. I can now plot those points. 0, 0, I'm focused on x and y now, not t. 0.5, 0.25, 1, 1, 1.5, 2.25, and 2, 4. Think of those as points. 0, 0 is the origin. X equals 0.5, y equals 0.25 is about here or so. Well, a little bit over there, close enough. 1, 1 is about here. X is 1.5, y is 2.25, would be right about here. X is 2, y is 4, would be right about here. In fact, the graph of this is a parabola. It's the parabola y equals x squared, which makes sense since y does equal x squared, because x equals t and y equals t squared. But it's really more than just a curve, it's a motion. The particle is moving along this curve as time goes by. It's really a good idea to put arrows going along this curve. And realize you're at this position when t equals 0, this position when t equals 0.5, here when t is 1, here when t is 1.5, and here when t is 2. So that tells you, intuitively thinking about this, the particle's speeding up. It's going faster and faster. The speed is not constant here. Let's go ahead and graph this in parametric mode. X equals t, y equals t squared. T goes from 0 to 2. Make a window that can show all this, like 0 to 5 for x and 0 to 5 for y. Graph it. Now watch, I'm about to hit graph. Watch how the speed changes. It's going to start out moving very slow, but then it will speed up. Ready? 1, 2, 3, go. Yep, it's speeding up. Maybe a little hard to tell. Let me try making the t-step even smaller. Now it'll go pretty slow at first. There it is. Going kind of slow, but it does speed up. That was maybe too small for t. It is going, you can tell now, it's going faster and faster. Of course, in real life, it's not a squiggly line like that. That's the calculator's pixels. Okay. Try one more. Let's make it 0.005. It is speeding up as it goes here, faster and faster. So again, the speed is not constant. Part B, show work to confirm the speed is this. That's just a formula I told you. The speed is the square root of f prime of t squared plus g prime of t squared, or if you prefer with Leibniz notation, that's the square root of dx dt quantity squared plus dy dt quantity squared. And by the way, these are not second derivatives. These are first derivatives squared. But f of t is just t, so its derivative is 1. And g of t is t squared, so its derivative is 2t. Square that, you get exactly what I told you should get. This thing right here. And by the way, this is not the same as 1 plus 2t. You can't take the square root of a sum like that. You got to leave it like this. When you integrate the speed, you get the distance traveled. And I do mean distance traveled here, not displacement, not change in position. How far have you moved along this curve? In other words, what's the length of this curve? From time 0 to time 2, it's this integral. You should know that. I told them that there. The goal now is to estimate that distance traveled with one of two possibilities, including units. Either go ahead and use your calculator, but describe what you do, or do a right-hand sum, those are sometimes called Riemann sums, using delta t as 0.5 and this picture here. I gave them the option of doing either one. You should be able to do either one. I might say do it one way or the other for you. Let's try it as a with the calculator first. You'd have to go back to function mode, not parametric mode. Go back to function mode. We are still talking about the parametric curve, but we're not integrating the parametric curve. We're integrating the speed. We're integrating this function. So in regular function mode, I need to plug in now the square root of 1 plus 4t squared, which of course, since I'm back in function mode, will be 4x squared. Go ahead and plot this. T goes from 0 to 2 here, or x goes from 0 to 2. How big does this function get at time 2? 2 squared is 4 times 4 is 16, plus 1 is 17. Square root of 17 is a little bit bigger than 4. So in my y scale, I better go higher than 4 like I have here. Here's the graph. This is not the motion. This is the speed. It's related to the motion. You can see it's going higher, meaning the object is moving faster over time. But it's not the actual graph of the motion itself. That graph is this one. But the integral of the speed does give you the distance traveled. So I could do it on the calculator. I could go calculate menu, integral, lower limit of 0, upper limit of 2. It'll calculate the area under the curve. About 4.65. That's the distance traveled in whatever units are given here. Time is in seconds and distance is in meters, is what it says up here. So this integral would be the distance traveled in meters, about 4.65. If you're going to do it with a right-hand sum, you're really adding up areas of rectangles that way. And notice for each subinterval, I'm using the right endpoint, like on this first subinterval, I'm using the right endpoint to go up to the graph and over. And that's the approximating rectangle. Excuse me. Same for the other subintervals. I go, in each case, go to the right endpoint and go up to the graph. So now just find the areas of those rectangles. Symbolically, it would be best to write these as speed of 0.5 times 0.5. That's the area of the first rectangle. The base is 0.5. The height right here is speed of 0.5 plus speed of 1 times 0.5. That's the area of the second rectangle right here. Its base is also 0.5. Its height right here is speed of 1 plug in 1 right there into the speed function. The second coordinate right there is speed of 1. That's also the height of the rectangle. Speed of 1.5 times 0.5 will be the area of the third rectangle right there. And speed of 2 times 0.5 will be the area of the fourth rectangle. So now you just got to plug these numbers into the speed function. And really, I can add up all those speed values and then multiply by 0.5. I can factor out the 0.5 here. Speed of 0.5 is square root, I can type it correctly, of 1 plus 0.5, square root of 1 plus 4 times 0.5 squared, about 1.414. Speed of 1, plug in 1 here, you're going to get square root of 5, right? 4 plus 1. Square root of 5, 2.2361. Speed of 1.5 will be square root of 1 plus 4 times 1.5 squared, 3.1623. And then finally, speed of 2 will be square root of 17. Plug in 2 there. We're going to get 1 plus 4 times 4 is 17. Take the square root. 4.1231. Don't forget to multiply all that by 0.5. This is going to be too big because the areas of these rectangles are too big because the function's increasing. A right-hand sum is going to be too big. But that's what I told them to do here. 1.14 or 1.4142 plus 2.2361 plus 3.1623 plus 4.1231 times 0.5. The right-hand sum approximation is about 5.47 meters. Remember the actual value that we got with the calculator, what was it, 4 something? I forgot. Get that? Graph it again. Calculate the integral. The actual distance traveled was about 4.65. The right-hand sum is too big. But it's an approximation that comes from a right-hand sum. Can I clarify anything here?
So you said that you might just choose one method for us to solve this on the
Yeah, you
exam?
should be able to do it either way. So make sure you practice both ways.
Okay.
All right, those are the problems about integrals. And that's what we mostly had time for here. Got 8 minutes left. Let's just highlight some other things. We don't have time to go through details. This one you can see is about L'Hopital's rule. This is a 0 over 0 indeterminate form. ln of 1 plus 0 is ln of 1 is 0, and 2 times 0 is 0. I guess we can quickly do this. L'Hopital's rule says differentiate the top and the bottom individually, not the quotient rule, and try to take the limit of what you've got left. Now, sometimes you have to use L'Hopital's rule again, but in this case, we don't. We can plug in x equals 0 here. It's a nice continuous function at 0, and the answer is 1/2. You could check that by graphing this function and seeing that it approaches 1/2 as x gets closer to 0. This one is about finding critical points and confirming local maxes and mins with the first derivative test, looks like, and maybe even the second derivative test. I was helping them here. Should be able to do that even without help, although it takes practice. You'd want to make sure you could differentiate that and factor that derivative like this. I was trying to help them along and also make the grading easier by giving them help here. But, this is the kind of problem where we made a number line and mark off the critical points on the number line and test the sign of f prime. With this example, f prime is going to be positive here, negative here, positive here. That means f itself is going to be increasing, then decreasing, then increasing. And you're going to have a local max at -2 and a local min at 3. I didn't ask them to optimize this over some closed interval. I could have. And remember that if I give you a problem like that, you also need to check the endpoints if you're trying to find a global max or global min. This one is a 2-parameter family of functions. A and B are parameters here. Trying to find the critical points in the minimum value in terms of A and B. And I told them the answers here. You should be able to work it out. I'm pretty sure these answers don't involve any mistakes. That's something to work on your own here. This problem here is related to rates. You don't see a ladder, but we could draw one quick. It's a 5-meter long ladder. So that's 5 meters here. Leaning against a wall. The bottom of the ladder is sliding away from the wall at a certain rate, 0.2 meters per second. That's how fast this is moving to the right. How fast is the bottom of the ladder sliding down the wall? There's a typo here. It should be the top of the ladder. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 3 meters away? It's a related rates problem. You'd maybe want to call this x and this y and realize that x and y depend on t, time. They are changing over time. The 5 is not. The hypotenuse of that right triangle is always 5. But x and y are changing over time, right? X is increasing because the bottom of the ladder is moving to the right and y is decreasing. If you differentiate them with respect to t, you're going to get this. And you'd want to make sure you do this kind of thing before plugging any numbers in. In the end, you will plug in x equals 3. Let me now label that as 3, though. You will plug in x equals 3 in the end. And you will plug in dx dt as 0.2. But those aren't constant necessarily, and certainly this is not constant. You're trying to find dy dt, or actually its absolute value. The answer is going to be positive. You're asked for how fast it's sliding down. You're going to actually, your goal is to find the absolute value of dy dt at the indicated moment in time. And by indicated moment in time, I don't mean you're plugging in t equals something. I mean you're at the moment in time when x is 3 and dx dt is 0.2. This one is about minimizing surface area. We did problems like that. You need to use the constraint, the fact that the volume is fixed here, to be 10 cubic centimeters to solve for h in terms of r. It would be h is 10 over pi r squared, and then substitute that back into here for h to get a function of just r that you would differentiate with respect to r to find the critical point. I'll leave that to you. We did problems like this maybe what, about 2 weeks ago or something? Maybe when I was still sick. That's most of what you're responsible for. Again, you don't need to do a problem like number 5. You also don't need to know how to do a problem like number 14, a differential equation. We haven't talked about that. And you also don't have to do one like number 18. We haven't had time for that. It involves something called the constant function theorem. So for those types of problems, or those spots in your exam, I give you different problems. So the exam basically covers chapters 4 and 5. Applications of derivatives and integrals, what we've learned about all those things. Optimization, related rates, L'Hopital's rule, parametric curves, integrals. Okay, so rework through these problems, and also there's a second old exam that's got some answers on it as well. We'll see you on Wednesday.